introduce Ali Kavis. His PhD at EPFL and is now an IFML postdoc and is part of Aryan Mokhtari's group. He's doing a lot of really exciting work in optimization.
Hey everyone. So this talk is going to be a bit more different than the first three talks that you've seen. I'll focus on optimization, specifically parameter-free methods for second-order optimization where we have a min-max objective. So this is a joint work by Ruichen Zhang, Truicheng Jin, Sujay Sanghavi, and Aryan Mokhtari, and Ruichen is over there in the audience. So let me quickly start with the basic definition of the problem. Now we're going to have an objective where we have two parameters, and we're going to minimize. We want to minimize this objective in x and maximize it in y. So this, in this very general form, it arises in many situations. Like a good example, I believe, is the primal dual optimization, where you have a comics problem with constraints. You want to solve the Lagrangian. You write in this primal dual form and then solve it. GANs have this formulation, although it's a bit different than this multi-objective idea. It also falls in the same category. And there's some reinforcement learning problems in there where you have a linear program and you deal with its dual. Same for multi-agent games where there's multiple agents with different objectives where they want to maximize their gains. So to maybe formalize some examples, let's say that we have a comics function, we want to minimize it, and we have an equality constraint. This is like a linear equality constraint. So one thing you can do is you can write the Lagrangian of it, where you would like to penalize if you're infeasible, and then you just want to maximize over this whenever the constraint is not satisfied. So you can solve this in this iterative min-max manner. And maybe a more relevant example is, so when you have generative adversarial networks, you have two basically networks. One is the discriminator, which tells you whether some data comes from a distribution that you want or not. And there's a generator which starts with a noise and then generates some data. And then there's kind of like a competition between them. Discriminator wants to know if this is a fake, let's say, data, as in images. And the generator wants to fool the discriminator, and there's this min-max game happening. So for this talk, we're going to focus on a much simpler case than this one. And let me actually quickly formalize the setting for you. So I'm going to assume my objective function is going to be convex in x, and it's going to be concave in y. And the way we measure our performance is basically we want to find a saddle point, where if we move away from the saddle point, we're going to have a worse value. So the way we measure is the restricted gap function. So there are two things that we need to think about this. So the gap is going to be 0 when we're at the saddle point, and it's going to be a positive value if you move away from it. And we need, for this unconstrained problem, I would like this to be an actually restricted, a constraint gap. And the reason is, if we have a linear game, like a matrix game, let's assume it's just x, y, right? And if you didn't have any constraints on x and y, this is going to be, unless you're at the origin, this is going to be infinite. This is vacuous. You don't want to do this. So we just put some restrictions. And what we want to do is all these sets, they're going to contain the saddle points. So this is one assumption that we're going to have. But what I want to focus on is, from this min-max perspective, I actually want to simplify the way we write it down, because this is easier for analysis, easier for display. So let's assume we're going to concatenate our variables and the gradients. So what we do is we concatenate x and y, and then we concatenate the gradient with respect to x and with respect to y in this following way. So when I do this, there is this one-to-one relationship between convex concave, small f, and our operator being monotone. So this operator is going to satisfy this. And this might be similar to you when f is actually gradient of some convex function. And now we need to reformulate the problem, because if you want to solve this min-max problem with this operator form, it kind of changes. So what we want to do is we want to find some set stars such that this holds. And then one way to look at it is, so assume that, again, this is like the gradient of a convex function, right? So if you move away from the supposed point of optimality, then you shouldn't find any descent, the direction of descent. So if this is positive for any z around the neighborhood of z star, then it means z star is an optimal point. So you cannot make any progress when you move away from it. So this is how we find this like one-to-one connection. And the performance, in terms of performance measures, we're still going to use the gap. And the way we do it is, so for such problems, the way we would analyze is through the regret. So what happens is we have some algorithm which solves this problem in the middle of this new formulation that we have. And then this is going to generate as a sequence of points. And then what we're going to do is we're going to compare the performance of the sequence of points with respect to some fixed comparator. This can be any point, but let's assume this is some saddle point, right? And then one can easily show that for any averaging sequence where the sum of theta t's are going to be 1, this relationship holds. So we can go from this regret definition back to the gap and everything holds for us. Okay, so this is the basics of how this operator scheme is going to represent our min-max problem. So let me do a little recap of the literature and what we're going to do. So as I said, our focus is going to be second order. So let me give you what happens in the first order, what happens in the second order, and then let's point out some open problems and how we solve them. So the fundamental assumption that most of the work in this field does is I'm going to assume the gradient of the min-max objective is Lipschitz continuous. This is equal to my operator being Lipschitz itself. And it satisfies this property. So the way to look at it is we're actually kind of saying that the operator is nicely behaving. There are no abrupt changes in its value once you're moving away from like between close points. And this is actually very well studied. The people have been trying to solve this problem since late 70s, early 80s. And we know that the best case scenario for you to find a point that, a saddle point of this problem is through the rate of 1/t. And in fact, there are many algorithms which are known to achieve this. So technically speaking, there is not too many things to do. And let me give you 2 algorithms that does this. So what is interesting about these algorithms is that they are using multiple calls across the iterations to make their steps. And maybe I can actually explain it why this is actually an important idea, rather than having a single call algorithm. So what extra gradient does is we start at some points at t, and then we're computing a direction of progress. So once we're dealing with operators, it's not very meaningful to call a direction of descent. So let's call this a direction of progress. And then we take a step and go to this middle point. So what we do is we go back to our initial point, but now our direction of progress is computed with respect to this middle point, and then we go to the next one. So this is, we can say that there's some correction happening at some point. And there's some variance of this, which is called mirror prox. And the difference between this extra gradient and mirror prox is instead of using Euclidean norms, if you use some Bregman divergences, this is when we get mirror prox, when we map everything to another space and then back. And extra gradient is when everything in the Euclidean case. So another variant, which is doing some sort of correction in its own, is called the optimistic method, or forward reflected backward method. So what it does is the correction effect is still there, but what we do is we're using previous calls. So we're looking at how the direction changes between the iterations, using this as a correction to our step, and then take the next step. So these are important, especially in the case that I showed you in the bilinear case. When we have AXY or XY, then these are necessary because if you just take gradient step, you'll start diverging because you're circling out of the saddle point. But when you do this, with a correct step size eta t, you will slowly converge to the saddle point. So this correction idea is kind of important for this min-max problems and this operator problem. Okay, so what happens in the second order case? So in the second order, we're not going to assume that now the gradient is well behaved or the operator is well behaved. I'm going to assume it's Jacobian, or the Hessian of the min-max problem is well behaved. So if you go back, so this assumption, it actually tells us that the Jacobian is bounded, but it doesn't tell us how well it behaves. So essentially, this is a more restrictive case. We're not saying that, okay, our operator has a curvature which is bounded. It's more like the curvature is well behaved. It doesn't do abrupt changes. So in this setting, the theory tells us that we should be able to go faster. We should make faster progress. But to do so, the existing work has 2 strategies. The first strategy is the line search methods. So the reason why you need line search is a bit different than the classical optimization methods. If you're familiar with the literature of optimization, first order optimization, line search is done because we don't want to know certain parameters of the problem. How smooth the problem is, this Lipschitz constant here, right? So line search gives us a good enough step towards which we can make progress. And then we can do this without knowing the Lipschitz constant. But for these problems, this is necessary to achieve the faster rate. And then I'll like in the next slides, I'll explain why this line search is actually important. So the problem, as we can guess with the line search, is let's say a downside of it's not a problem, is that every iteration you need to do some iterative scheme to compute a good step size for your method. And then this requires additional computation of f and its also derivative. The second set of methods is the subsolver based methods. So what happens here is these methods do not have a closed form solution to compute the next point. You actually need to solve an optimization problem to go to the next one. And then since there's no closed form, you need to do some subsolvers for it. And this is where the extra computation comes into play. So both of these methods are capable of achieving this rate. But every iteration, they're actually doing some additional work. And we want to avoid it. This makes the algorithm complicated. This makes the per iteration cost higher. So what we want to do is we want to focus on the first class of problems, the line search problems, where they have a closed form solution for the next point. And we're going to eliminate line search in some smart way such that the algorithm is simple, we get the same rates, and then also, practically speaking, we are seeing some advantages in certain regimes. So the optimal rate here is going to be T2 1.5. We want to avoid line search and subsolvers. And one important thing that we want to do along the way is we don't want to know any parameters of the problem. So in this case, this is going to be the Lipschitz constant. We don't want to know Lipschitz constant. And what we're going to do, we're going to estimate it in our own way. And then we just want the algorithm to be simple. So before I move on to the algorithm itself, I would like to talk more about the optimistic method, which is going to be the base for us. And I'll try to motivate why optimistic method is important and how we're going to make this optimistic method higher order method. So everything goes back to proximal point. So proximal point algorithm in itself is an implicit algorithm. So what we want to do is we just start at some point zt, and we go to the next point by computing the gradient at the next point. So this is kind of like this circular problem that we don't know how to solve. But let's assume there is somebody who tells you that, hey, I can give you these points every time that you ask me. And then I can do this for any step size that you want. So if this is the case, then you would have an algorithm which goes infinitely faster, because your convergence rate will be a function of the sum of your step sizes. But this is intractable for many problems. If you're not linear, you should forget about this method working. So what we want to do is we want to approximate this quantity. We want to have a good approximation such that combined with a large enough step size, we can make good progress in the direction that we want. So the idea is very simple. So we want to predict what the next point is going to be using the information that is available to us at the current point. And then we know that this prediction is going to have some problems. It's not going to be 100% correct. So we want to actually correct this prediction by looking at how well we did in the previous step with our prediction. And then we're going to scale those things, combine them, and then hopefully get a nice correction, which actually this optimistic method does. And this correction idea is also similar to extra gradient, but it's a bit technical to say if there's any equivalence. So this predict, correct, and scale idea is what we're going to do. And like formally on the optimistic method, so my prediction of the next point, if I was in the first order setup, my prediction is going to be this. I would say that the gradient, the direction at the current point is going to be a good estimate. But since now I have more information available to me, I'm going to use a linearized version centered at zt to predict the next point. So supposedly, higher order methods with a better prediction should get me a faster rate. This is where it starts, with the faster rate thing. And then I compute the correction. What I do is I get my current point, I look at its prediction, and then I look at the difference, how well I did in terms of the directions and magnitude. And then I combine these things, my prediction and the previous error, together by scaling. So supposedly this is going to be a good estimate for the direction at the next point, right? So everything combined, rearrange, we get this second order algorithm. So this is like, if you're familiar with the first order literature, this is very similar to a regularized Newton method, where we regularize the Hessian, so to say, with some identity. You can also scale this. And then we just put our direction with its correction in there, and then we do our step. Okay, so let's go back to the line search idea. So why do people need line search with this kind of scheme or any other scheme? So what happens is, I'll explain this later in a few slides, but if you want to go at the faster rate of t to the power 1.5, we need to make sure that our prediction error is actually small. So the way we measure it is our prediction error at the next step, which is actually the difference between zt+1 and its prediction at the current point, right? We want this to be smaller than how much progress that we make. And then we're scaling our error with the step size. So if we were in this proximal point algorithm, we can satisfy this with alpha 0. We're in the perfect case. We can go as fast as we want. And we can show that optimistic method, if we know the parameters in the way, in a certain way, then we can show that this can actually, optimistic method achieves this with 0.5. But there's still a problem. This condition is implicit. We still don't say how to select eta such that this is satisfied. A good rule of thumb is, let's make our step size so small that we always satisfy this, which is going to be a valid step size and we will make progress, but it's not going to be fast enough because the whole trade-off is, okay, make sure that this error condition holds so your prediction error is small, but you should also satisfy this with large step size so you're making large steps. So to actually do this, to address this cyclic relationship, we develop a new method. Okay, so just to go over the goals, we want to be optimal, no line search, no subsolvers, simple algorithm, and I don't want to know any parameters of the algorithm. So here's the algorithm that we have. So here, at every iteration, I'm going to compute my prediction error at the previous case. And then let's forget what happens here. And then I'll just do the step as I described before. So now I introduce a new parameter here. So this is, under certain settings, this is not necessary. But if you want to be completely parameter free, then this is an important addition. So what we do is we're taking the Jacobian of the problem. We're just regularizing it. We're making it nicely, behaving even nicer, right? This is gonna how we do the scaling. And then we take our step. So the important thing is, how do we select the step sizes, the eta and the lambda? So these are the parameter definitions. I'll explain how we get them. So the way to look at it is, lambda in a traditional sense is the inverse step size, right? If you know the Lipschitz constant, what you would do with your method is you would just put it in the inverse and do your steps with the gradient method. So this is more or less the inverse step size that you have. So if you know Lipschitz constant, just plug it in its place. If you don't, you can actually estimate it using the smoothness inequality. You just use an estimate. This is not going to be accurate. This is probably going to be off. But the theory tells you that if you just keep doing this in an incremental way, in a way that you actually control the monotonicity of this parameter, this is going to be a very good estimate for you. And then you have this other step size, the second one. So again, I'll explain how this is obtained. But a good rule of thumb is this is a self-balancing step size. So assume that you're converging. As you converge, your errors are going to go to 0. Your operator is going to shrink to 0 in an unconstrained setting, right? So, and then if there's too small, then in the next iteration, you'll have a very large value for your step size eta t. But then, since it appears in the denominator in this recursive manner, the eta t+1 is again going to be small. So if you let the algorithm behave on its own, it's going to oscillate a little bit, and it's just going to converge to some nice value. And it's going to decrease over time because it's going to increase over time because of the decreasing quantities over here. So, okay, how do you obtain this? Where does this come from? So for this one, I need to explain where the error condition comes from, and the error condition is going to lead us to this one. So if you're familiar with regret analysis or min-max problems in any way, this is a pretty classic upper bound for your regret. So here, for simplicity, I just picked one of our step size to be a constant, so it makes our jobs easier because certain terms are going to telescope the distance to the solution, for instance, and we're going to end up with this one. And then the major error in our execution is going to be this. So, and I think we can see where this error condition comes from. So what we want is, if this error is small every iteration, then this error is going to go to 0, or it's going to be a negative value even. Actually, for technical purposes, we want this summation to be negative of some sort. But let's say that if this is small, this is going to be small or 0, and then we want the convergence that we want. Everything boils down to this one. And then when we rearrange the terms in some way, this is what we're going to get at the end. Okay, so we rearrange again, and then obtain this. Still, we haven't solved the implicitness problem. Still, the step size needs to know the next error, the next point. So here's the idea. Instead of satisfying this, why don't we find an upper bound to this term as a whole, such that we save it from all the terms with t plus 1, and then we claim that this new upper bound is going to be smaller than or equal to 1. And then actually we're going to equate it to 1 to have the largest step size possible. And to do this, it's pretty simple. We just go back to the definition of the error, and then the error is going to be this. And this is where we use the smoothness inequality. We use it and then obtain something in this form, where these two are going to cancel. And then we're going to use the definition of our update rule and then get this upper bound. So once we do this, everything is going to be free of any quantity at the next point, t plus 1. So everything now is an explicit quadratic function of the step size. So what remains is just solving it. And then once we solve, okay, let me go back. This is actually what we're going to obtain. Okay. So let me wrap up with the convergence rates and some experiments. So the first case, we assume that we know Lipschitz constant. We're just going to test if this adaptive strategy holds. And what turns out is that with this thing, with the setting where f is monotone, its Jacobian is Lipschitz continuous, and then you can show that your iterates are going to remain bounded within some neighborhood of the initial distance, and then you're going to get the rate that you want. So for the second case, I'm going to need an additional assumption, which I have never talked about, which is that not only the Jacobian is Lipschitz continuous, but the operator is Lipschitz continuous, meaning the gradients are Lipschitz continuous. So the reason for that is to obtain this here. So what most people would do for parameter-free methods is that they would assume the iterates themselves are bounded without just showing that they are. So what we do is we make a milder assumption. Let's say the gradients are well-behaved. They're not bounded but well-behaved. And if they are well-behaved, with some algebra, you can show that the iterates stay bounded. Once you have this, the rest is very similar to what you would do if you know the Lipschitz constant, and you will get this rate with some additional factors that you do. So the parameter-free literature tells us that if we wouldn't have this assumption, probably we would need to suffer some log factors in here. And so that was our solution. We couldn't get it done in the other way, but I think this is like a good step forward because we know nothing. We just make a very mild assumption, and then our algorithm works in a very simple way. So let me finish off with some experimental results and a few remarks about how this adaptive strategy might be important. So here we just want to solve a very simple min-max problem. And here our assumptions are going to hold for the second order Lipschitzness. And so what you see is, so these are our methods. So this is our method where we know the Lipschitz constants. This is the parameter-free method. So these two are, this is a line search method, and this is like a hybrid between a parameter-free and the line search. So the thing is, both of these methods are going to spend additional iterations to compute a good step size. So the difference is, once you drive the dimension higher, this is where you see the advantage, because no matter what high the dimension is, we don't do this iterative procedure where we need to call the gradient or the Hessian or any other parameter, any other quantity from the algorithm. We just do the execution in the way we want. So once the dimension becomes higher, this gap increases. But if the dimension is small, then this is where the other methods are going to be better than us. So there's this trade-off. So if you want to show that if you want to show that our method has an advantage against the line search based methods, then this has to be in the higher dimension setting. And another thing that is really nice is we don't need to worry about the initialization. So what we tested is, so let's ignore this for a while here. So we just said that, okay, let's get some random estimations of the Lipschitz constant, some random values, and then just put them in place. So for the original Lipschitz constant being small and large, we see that our method roughly behaves in a similar way, no matter how you initialize. But what's so interesting is you don't need to worry about some random values, actually. You can do this randomized initialization that we called, which is practically computing this value for here, the initial value and a small perturbation of it. So you just initialize at a random point, perturb it and get another point. Just use this heuristic to estimate your Lipschitz constant and also compute the parameter accordingly. And then your method is going to work. You don't need to even tune it. So I think a good takeaway message is the application of min-max problems, especially in second order, pretty restrictive. But this idea of using this Lipschitz estimation and using an adaptive parameter is going to actually help you with not the execution, but also the initialization. So these similar ideas can also be used for simple minimization problems. You can use this for SGD. Just tune it a little bit or some gradient algorithm, and then you will get some good initialization and also some good performances under certain circumstances. So yeah, that's the end of my talk. And if you have any questions, I can have some.
Questions?
Maybe could you explain a bit more how you would extend this to SDG or the
Okay, so with the SGD, the main issue is going to be this one is in a denominator, right? Because these are going to be stochastic values, and when you take the expectation, it's not going to work. So one strategy that people do is they deal with, okay, they take the difference between what would be the value of this if everything was deterministic, and take the difference between the stochastic value. So you're actually taking the difference between the expectation of the denominator and the real value. And then you do this new analysis. But I mean, it's going to complicate the analysis too much. I try to take a look, it's very difficult. But what you could do is apply this to deterministic first order methods. And a similar idea is going to work, first order, second order. In practice, it definitely works. Theory requires some additional assumptions.
Have you tried some experiments?
I haven't tried stochastic experiments. But in deterministic, it gives you reasonable performance. It's just like the proof is a bit involved, or you need additional assumptions. So there's like a trade-off.
Okay, thanks again.